Hello everyone. In this video I'm going to do two examples that have to do with introduction to that mass oscillator or mass spring oscillator. So let's see, it's two examples from introduction to mass spring oscillator. Let's say we have an IVP that is 5 times the second derivative plus 20 times the function equals 0. And because this is a second order, we're going to need two initial conditions, unlike what we did previously, which is the first order, and we needed one initial condition. All right. And so we need, this has two requests. The first one is to verify that y of t is equal to sine of 2t plus 5 of cosine of 2t is a solution. Okay. Then a second request will have to do with finding a maximum, and I'm not sure if you, of course, if in calculus you've done the maximum, but I'm not sure if you faced the type of the equation or trigonometric equation that we're going to do. So let me know. Okay, so let's deal with the first request. I think to verify that this is a solution, we're not going to verify only the function, the equation. We will also verify the initial conditions. So let's get the first derivative. Using chain rule. Alright, so initial conditions, y of 0 equal 5. Right, let's see, y of 0, so that's the question. Y of 0 is sine of 2 times 0 plus 5 cosine of 2 times 0. Sine of 0 is 0, 5 times 1 is 5, so yes. Now second one here, we have the first derivative, so 2 cosine of 2 times 0 minus 10 sine of 2 times 0. Alright, and that's a 2, so it does check. Okay, so the next thing to do is to find the second derivative. Okay. Yeah, you could find the first, second, then start checking either way. But I just want to emphasize that we're also checking the initial conditions. Okay, so now that we have this, let's check the equation, which is let's rewrite. So we're going to use the second derivative and the function. The first one is not used. That's negative 20, that's a 20 out, that's negative 100, that's a positive 100, so yes. Okay, so that's done. Now let's look into a request that it says find a maximum of this function, or to abbreviate y, and the absolute value, because this thing is it oscillates, and if you look at the equation, we don't have y prime term, which means the damping coefficient is 0, which means this thing oscillates up and down, so we could have another much lower point and another higher point. So we're using here this absolute value. Okay, and the request is for any t. Alright, so you've done in calculus that if you're looking for a critical point, you're going to set the derivative, the first one, to 0, which gives us 2 cosine of 2t minus 10 sine of 2t equals 0. And here I would encourage you, of course, to pause the video and try different ways, try the trig identities, and see how this works out. The cosine 2t and sine of 2t create a challenge, which is, and I think if you use a computer to solve this, it will give you some approximated solution at the end for this maximum. So I will use a different method here, and I will try to even take a shortcut in it. I'll show it. So one way I can connect, because the idea when you solve these trig equations is to connect these functions. One way to connect them is the tangent. So if cosine of 2t is not 0, and we can go through that detail, but for the sake of this video, to make it short, let's say there are a couple checks to do, but if cosine of 2t, of course, not 0, we can divide by cosine of 2t, and of course we can verify whether the maximum is missed or not missed, this and that, and that could be a problem when you're dealing with x-intercepts. So you don't want just to divide by a function. That's one idea that is well known in math. You just, for example, if you have x cubed minus, let's say, even x squared or something, or you have x times x minus 1 equals 0, maybe that's a quicker way to show you. Yeah, so probably the quicker way to show you is this one. So we know how to do this. You factor and you get this form, then you set h to 0. But what happens if you say I'll just divide by x? You get x minus 1 equals 0 again. Then you miss the chance of including that x that equal to 0. So x equal 1, you see that's not correct, and we miss the other part that is this. Okay, so that's kind of the idea. This is not a generalized method that you can always divide by a function. It depends on what you're doing. Alright, so tan sine 2t over cosine of 2t equals 0. Um, 2 minus 10. Let's switch to tangent. 0 divided by 2. So tangent of this is 1/5. Alright, so that means tangent of 2t, let's write it here, is 1/5. We know using the arctan means 2t is arctan of 1/5. We can add, of course, the npi every other, then you will divide by 2. That's kind of the process. Divide by 2 to find t, and that's the way to solve. But I'm gonna be just curious here. What happens if I just leave it as 2t? Let's show you that. So our 2t some angle, you can just look at it as one thing. That means arctan is 1/5, and as I mentioned, because this oscillates, once you have the maximum, it happens again and again, so we don't really need that. Okay, so 1 and 5 because of tangent, opposite, adjacent. Then 25 and 1, 20, so this is square root of 26 when you do the Pythagorean theorem on this right triangle. Alright, so that tells us that sine, let's do maybe different color, sine of 2t of the angle is 1 over square root of 26. Cosine of 2t is 5 over square root of 26. Let's look at y that we are looking for. That's going to happen at this. Y is, let's see, I need to copy it from here, is sine of, that we verified. You see, so if I looked for t, then I will come back here and I'll multiply by 2. So by just skipping the 2t, because I know this is here, it's going to be used as 2t, I just left it that, and it's going to work fine. So sine of 2t now I know is 1 over square root of 26 plus 5, and cosine of 2t is another 5 over square root of 26, so 1 plus 25 is 26 over square root of 26, which is square root of 26. So the max of y is that square root of 26. And that's how you find the exact solution. Alright. So now let's do the second example, and that will have to do with the synchronous solution or the resonance. And I think I'll pause this video and do in the next one. Okay, thank you.